The first paper that we have in this session is online. It's Safety Factor Analysis for Autonomous Route Planning. It's from Xiaoyu Li, who is Research Engineer of Seastel Marine Systems in Shanghai. Okay, roll the video.
Hello everyone, my name is Xiaoyu Li. I'm very glad to be here to present our research on safety factors of autonomous ship route planning. The paper's co-author come from Seastel Marine Systems Shanghai Company Limited and Shanghai Jiaotong University. In this presentation, I would introduce two case studies on environmental factor and congestion factor in route planning problems. Here goes a brief introduction for our topic. Intelligent and autonomous ships have become the focus in the international shipping industry. Autonomous route planning for maritime autonomous ship is a process to plan an optimal route along the predefined waypoints with the careful consideration of ship maneuvering constraints and environmental conditions. There are mainly two sides of planning techniques, the deliberative planning and the reactive planning. Safety factor considerations, including environmental factor and congestion factor, are important for the development of autonomous ships. Here goes the first case study. It is a real canal estuary area with strong currents, as the picture shows here. The estuary area always has strong currents, and the experiment is to find a path for ships to cross a barrier and dive here and enter into the canal. We employ a deliberative route planning algorithm to solve this task. This table shows the basic modules of our algorithm. We employ a modified rapidly exploring random tree, which is known RRT algorithm, to get sample waypoints, as the upper picture shows here. And the maneuver automation algorithm is used to generate dynamically feasible route segments, as the lower picture illustrates. Finally, a cost function is set up to search for optimal route. With the progress mentioned above, we can generate a suitable path in calm water. Then we create a current effect adjuster to tune the route according to the current condition in different area. As the picture shows here, we stretch the calm water route by the current speed to generate a new route. We want to make sure the ship has enough ability to resist the current's effect when tracking the new route. This picture shows our model test scenes. We set up a fully functional autonomous ship system with navigation, guidance, and control submodules. We put the ship at the start point and set the destination in the canal. The ship would automatically find a route and track it to the destination. Here are the results of the experiment. Firstly, as a comparison, we use the route planning algorithm without considering current effects. The left picture shows the planned route, which is a red line, goes into the center of the canal, while the right picture shows the real trajectory the ship made in the test, and the current comes in this direction. This is a video record of test 1. As we can see, the ship barely goes into the barrier, which is very dangerous. This is because the planned route doesn't consider the current effects. And in the test 2, we add the current adjuster into the algorithm. As the left picture shows, the planned route becomes quite different from the previous one. The right picture shows the real trajectory the ship made in the experiment, and the current condition remains identical. This is a record of test 2. As we can see, due to the effects of strong current, the algorithm generates different route to make sure the shape is away from the barrier. It is much safer than before. Our second case study is focusing on autonomous clearing avoidance in multi-shape encounter situation. The left picture exhibits our test model, which is also a fully functional autonomous shape. The right one shows the on-water test scenes. We employ a reactive planning algorithm combined with an intention model, which can predict intentions of surrounding shapes. This table here shows the main scheme of the reactive planning algorithm. We use dynamic window algorithm to find reachable state space, as the upper picture shows. And the motion control primitive algorithm is used to generate dynamically feasible route segments. An intention-based velocity obstacle algorithm is deployed to avoid clearing. Finally, a cost function is set up to make sure the chosen route is safe and meets the requirements of the international regulations for preventing clearing at sea, which is known as COREX. The intention model is set up within hidden Markov model. We build 4 hidden Markov models to separately represent Hipker's intention, turn life and rect intention, and stop intention. Using target shapes sway, search, and yaw speed to form observation sequence, and through forward calculation, we can find its most likely intention. Here goes how we modify classic velocity obstacle method with intention prediction. As the picture shows, once the target is expected to change its navigational intention, for example, green line indicates it will turn to its left to curse C prime, the clearing cone A or B, which is the classical one, would expand to the right line B prime. Because the new clearing cone is always no less than the classical one, the algorithm can make sure that it can accommodate to the potential change of the target. This is the result of on-water test 1. On shape, the green one in the video, has a complex encounter situation with 2 target shapes. The algorithm chooses a proper route to avoid clearance successfully. Here goes the result of on-water test 2. The initial state of target shape 2 has a slight difference compared to test 1. So the target shape would have different intentions in the encounter situation. As a result, our algorithm can successfully adapt the change by predicting other shapes' intention. Now we have a brief conclusion here. These people analyzed 2 important safety factors in autonomous route planning. For maritime autonomous shape, environmental factors, for example, strong currents, can significantly change the best navigation route in the same area. On the other hand, when sailing in multi-ship encounter situation, accurately predicting other ships' intention can help enhancing navigation safety a lot. This is all my presentation. Thanks for your attention.
Okay, thank you. Thanks, Xiaoyu, for highlighting the very important aspects of autonomous navigation, including the effects of the environment and encounters with other ships in complex conditions, which happen quite a bit. Both of those cases happen quite a bit around the Singapore Straits here, where we have very congested sea lanes. Okay, do we have questions? No questions online, so here's a question in person.
Hi, thank you for the thank you for the excellent presentation. I was curious, when you have the intention model, if you could elaborate on, aside of having a hidden Markov model to generate it, what kind of input data did you use for the intention prediction, and yeah, you obviously had to use only past information for it. It went a little bit quickly there.
Should I do a little introduction about that part?
You can explain a little bit, go ahead.
Okay. we build 4 hidden markup model to represent 4 different intention model, and we collect target shapes, historic date, yaw speed, search speed, and to form a series of time sequence data. And we prepare a lot of data to train this markup model. And after training, we get a well-trained model. And in prediction scenario, we use the historic data and put through in this markup model to calculate the likelihood of each prediction. And we choose the maximum likelihood of the intention, and we think it is the intention of the target shape in the next time step.
Okay, more questions? Actually, I have one question. For the first case where you had the current, how do you get the input of the current velocity?
Okay, this is a real-life problem in a river in Hangzhou East city in China, and people want to build a barrier in the canal to prevent sand and mud flushed into the canal. So there are a lot of work doing on this project. Some people collect the current data and annually changed in that area. And they set up the experiment scenarios to simulate the current there. And we set up our experiment with that data.
I suppose the current might vary at different times of the year or different times of day. So how do you take into account the variability of the current?
Yes, we have different current conditions annually changed. So we perform lots of cases through different current conditions. And one purpose of the experiment is to find on which conditions can the ship successfully pass into the canal, and on which conditions the ship cannot pass into.
Okay, great. Thank you. Any more questions? If I could have just one more. For the second case, which has to do with different ship encounters, different ships, larger ships or smaller ships, they have different maneuvering characteristics. Some they turn very quickly, some bigger ships, they turn very slowly. How can we adapt the algorithm to consider different types of ships and how to differentiate them?
Okay, that is a very good question. Different ships do have different maneuverability and hydrodynamic performance. In our case study, we focus on the little ship model in the experiment we used. We use that kind of model to build training data and train our prediction model. So in further step, we should build more kind of dynamic model to comply to different kind of shapes, and use this much more widely data to predict more accurate models.
Okay, thank you very much. If there are no more questions, I think we thank Xiaoyu again. Thank you.
Thank you.